Again, welcome to lecture 10-2. In this lecture, we are going to study what is concavity and also points of inflection. Again, this is business calculus, mathematics 200 at New Jersey City University. So again, our main objective today is to determine the concavity of the graph of a function at a point, and also how to find points of inflection of a graphs of a functions. Also, how to use the second derivative test to graph a functions. So first thing we will go through is what is a concavity, and also what is a point of inflection. So we have a concavity, either concave up or concave down. So what is a concave up? Here we say if a curve is said to be concave up on interval A and B, if at each point between that interval A and B, so we can see the graph here, at interval A and B, any point that is here, as far as the curve is above its tangent line, is concave up. Again, the tangent line is the blue line, and we can see that the curve again is above the tangent line, and that's what we call the concave up. So a curve is said to be concave up on an interval A and B. So in this graph, we have an interval between A and B. If at each point on that interval, the interval A and B, any point within that interval is always above, the curve is always above its tangent at that very point. So this is again our tangent. Again, we have our curve. Then we have 2 points showing. Then we have our tangent line. So here we can see that our curve again is above its tangent. And also concave down is opposite of concave up. Here we say that again, the curve is below, or the tangent is above the curve. So here we say if the curve is below all its tangents on the same given interval, let's say here we have a point C to D. So interval is between C to D. We say that again, the curve is, or the function is concave down. By looking at this very figure, we can see that the slopes of the tangent lines increase over the interval where the graph is concave up. You can see the slope increase. So here we say again, because the derivative of f at x, that's the first derivative of f at x, always gives us the slope of those tangents, it follows that the first derivative of f at x is increasing over the interval where f at x also is concave up. So we know that the first derivative of the function always will give us the slopes of that tangent, of its tangents. And since we know that the first derivative of f at x always increase over the interval where f at x is concave up. However, we know that the first derivative of f at x is increasing when its derivative of second derivative of f at x is positive. This we may say that the second derivative is positive if the concave up, if it concave up, or the graph concaves up. So this is how we find the concavity of a graph. We always have to take the second derivative. We remember finding the interval of increasing and decreasing between in a graph. We have a graph, we want to know the interval where it increases and decreases. We take the first derivative and then we test it. Then if it's greater than 0, it's increasing, less than 0, it's decreasing. Now, if you want to know if a graph, a specific interval in the graph is concave up or down, we need to take the second derivative. And again, we're going to see an example soon. So this happens when the tangent line are above the graph, as shown below, concave down. So this is in summary, this is what we have done so far. What is concave up and concave down? So here we say, assuming that the first and second derivative of a function f exists. So we know the function exists. And there's interval, let's say a and b. We say the function f is concave up on an interval if the second derivative of the function is greater than 0. So now we can see a little bit similarity with the increasing. In increasing, we can say that the function, the interval of that function is increasing if what? The first derivative of f at x is greater than 0. So here we say a function f is concave up on an interval I if the second derivative of that function is greater than 0, or is concave up at the point a and f at a, if again the second derivative of a is greater than 0. But the opposite, the function f is concave down on an interval I if the second derivative of the function is less than 0, and also concave down at the point a and f at a, only again if second derivative of a is less than 0. So these are the rules now. Now let's see an example. So example is given, they say, is the graph f at x equal to x cubed minus 4x squared plus 3 is concave up or concave down? We don't know. But first we have to have an interval. So A, the interval is between 1 to 0. B is between 2 to -5. So the first thing I'm going to do is to find the second derivative of the function. So we start with the A. We find the second derivative of the function. We have x cubed minus 4x squared plus 3. So using the power rule and also sum and difference, the first derivative will be 3x squared minus 4x. Sorry, minus 8x. 3x squared, 2 times 4 is 8. So, and 2 minus 1 is 1. So it will be 3x squared minus 8x. Then we look for the second derivative. So if I have 3x squared, then it will be 6x minus 8. So our second derivative is 6x minus 8. Now we know our answer now, the second derivative of the function. So the next thing is that we are going to substitute the interval. We have 1 and 0. So we say the second derivative when s is 1, it will be 6 times 1 minus 8, which give me -2. So the graph is what? Is concave down at 1 and 0. So we take the second derivative, then we substitute the first interval value. Here they give us the interval. So even if it's increasing, between 1 to 0 should be positive. So here we said again, the question given, f at x equal to x cubed minus 4x squared plus 3. Then the question is, we want to find out if this function is concave up or down between two intervals here. We have A is between 1 and 0, B is from 2 to -5. So first we find the second derivative of the function, and we got 6x minus 8. Now we substitute 1. Now the rule said that if second derivative of the function is greater than 0, then we have concave up. If it's less than 0, we have concave down. In this case, we get -2, so it's less than 0. So we said that the graph is concave down. Now B, we have the interval of 2 and -5. So we decided to use the 2. And we have 4. So 4 is greater than 0. So we say the graph is concave up at 2 to -5. And we can see from the graph here. Now previously we have, I think it's 1 to 0 here. So let's look. We can see that from 1 to 0 is concave down, because the tangent line will be here. Now from 2 to 5 is concave up. This is it. So let's do a point of inflection. Again, as we said earlier, there's not much examples to do in concavity. Concavity, always we want to find if a function is concave up or concave down. Concave up means the curve of the graph is above the tangent, it's tangent. And concave down means the curve of the graph is below the tangent. So the tangent line will be above it with any points within the interval. Now, how do we find it? Concave up or down of a function? We take the second derivative of the function, then we test it with the first interval. If the value is greater than 0, that means it's concave up. If the value is less than 0, that means it's concave down. So let's go to point of inflection. Point of inflection also is where the concavity changes. So we may have a graph where the concavity changes from up down, and that very point is called the point of inflection. So a point of inflection, a point x0 and y0 on the graph of function is only called a point of inflection if the curve is concave up on one side of the point and also what, concave down on the other side. So this means point of inflection is the point where the graph changes from concave up to down or down to up. And that very point is called point of inflection. So we still take the second derivative at this point, and always will be 0 or undefined. So in general, we find points of inflection and formation by concavity as follows. So here we have a question here. Say, find the point of inflection of a curve and the intervals when it is concave up and when it's concave down. So the graph is given to be, or the function is given to be y equal to s to the power 4 divided by 2 minus s cubed plus 5. So what do? I find the first derivative, and I get 2s cubed minus 3s squared. We use the power rule here. We have 4s cubed divided by 2. 2 going to 4 is 2, so we get 2s cubed. Here we get 3s squared, and the derivative of a constant value is 0. Now I'm going to take the second derivative. I have 2s cubed, so it will be 3 times 2 and 3 minus 1, so we get 6s squared. Then here will be 3 times 2, 6. 2 minus 1 is 1, so it will be x. So now I got my second derivative. What we need to do now, we know the interval. Otherwise, yeah, they say set the second derivative equal to 0 and solve for x. The potential point of inflection occur at this value of x, at values of s when f at s is defined, and the second derivative at s also is undefined. So you can see that here when we get the answer, again, this is different concept from the concavity. When I find the second derivative, what I have to do, take one of the interval points, the beginning point, plug it. If you get the solution is greater than 0, that means it's concave up. If it's less than 0, it's concave down. But when we are looking for the point of inflection, after we find the second derivative, we have to equate the equation into 0. So here I have 6s squared minus 6s. That's the second derivative of the function. I will say everything equal to 0. Then I will solve for the value of x. So 6s squared minus 6s equal to 0. Then we solve for the value of x. The value of x gives us 0 and 1 because we have 6x, s minus 1. So we will say that the second derivative s is defined everywhere. Is defined everywhere. Now the question now says find the potential points of inflection. I use 0, 5, Then 1/9/2 are potential. Then the sign diagram, we know concave off means positive, concave down, negative, concave up again, positive. So again, this is how we find the point of inflection. You have the function is given. In point of inflection, we don't need to find the interval. Interval don't need to be given or find. We find the second derivative, we equate the equation to 0, then we find the value of x. Then we test it and see second derivative of x value 0, what it will give me, and also 1. So I can see that here, when I put 0, I will get -1. And also when we put 1, we should get somewhere around 5 or so. No, 0. So we can see that the interval will be 0 to 5, 1 to 9, 2. So again, a graph of this is given. We should know that the point of inflection was 0 and 5 and 1 and 9, 2. The point of inflection at 0 and 5 is a horizontal point of inflection because first derivative of f at x is also 0 at s equal to 0. So this is another example of a water purity. Here they say, suppose that a real estate developer wishes to remove pollution from a small lake so that she can sell lakefront homes on a crystal clear lake. The graph in figure 10.18 shows the relationship between dollars spent on cleaning the lake and also purity of the water. So we can see that by just looking at the graph, I can see that the more money we spend, the more purity the water becomes more pure. So the point of inflection on the graph is called the point of diminishing returns on investment. So when we are dealing with investment, it's the point of inflection on the graph. It's also called the point of diminishing returns when our returns start to decrease on her investment, because it is where the rate of return on an investment changes from increasing to decreasing. Now we should show that the rate of change in the purity of the lake, the first derivative of f at s, is maximized at this point, x equal to c, assuming that f at c or first derivative of f at tc is defined. And because x minus c is a point of inflection for f at s, we know that the concavity must change at x equal to c. So we say that if s is greater than c, then f at s is concave down. So second derivative of f at s will be less than 0. If second derivative of f at s is less than 0, means that the first derivative is decreasing. So the first derivative of x as a first derivative of c as its relative maximum. So now let's go to the second derivative test. Here we can use the information about points of inflection and concavity to help sketch graphs. So we can use the information about point of inflection, concavity to help sketch graphs. So for example, if we know that the curve is concave up at critical point where f at x derivative is equal to 0, then the point must be a relative minimum because the tangent to the curve is horizontal at a critical point. And only point at the bottom of a concave up could have a horizontal tangent. But on the other hand, if the curve is concave down, as we can see here, at critical points, then the point is relative maximum. So this is relative maximum because it's concave. So second derivative test, we are going to use a second derivative test to determine whether a critical point where f at x, the first derivative equal to 0 is a relative maximum or minimum. So to find the relative maximum or minimum of a function, first we have the function here. We need to find the relative maximum first and minimum. So we take the first derivative, equate it to 0, then find the s equal to -1 and also +3. S minus 3 equal to 0, s plus 1 equal to 0. So here we say no values of s makes the first derivative of f at x undefined. So we continue. The next step, we use -1, f at -1. When we do the calculation, we get 11/3. Then f at 3 also gives us -7. So the critical point will be -1, 11/7, and 3, -7. So the second derivative, then we go back to the function, the first derivative. So we get 2s minus 2. So we get 2s minus 2. So this is the example. You can see where so this is the concavity, changing from increasing to decreasing. So compare the advantage and disadvantage of second derivative test. We say the advantage of a second derivative test, it is quick and easy for many functions. Disadvantage means the second derivative is difficult to find for most functions. And also the second derivative test sometimes fails to give result. So this is a concavity from the graph of y equal to f at x first derivative. So the question is given to us. We have -s squared minus 2x. So the first thing we're going to do is to find the intervals on which f at s is concave down and also concave up. Then find s value at which f at s is a point of inflection. So first we should find the intervals on which f at s is concave down or concave up. Then we find s values at which f at s has a point of inflection. Then we check the conclusions from A and B by finding the second derivative and graphing it. So let's go through. We're going to find the first derivative. Again, these are the conditions. If the second derivative f at s is greater than 0, then we say concave up. If it's less than 0, concave down. So we draw the graph using a calculator in a software. Get it. So here, this is another example. F at s equal to 139 minus s cubed minus 3s squared. The first derivative, we're able to come up with s squared minus 2x. Then we plot it. Then we take the second derivative. So f at s, first derivative f at s, second derivative f at x. Concave up means increasing and positive. Concave down, decreasing, negative. Point of inflection is either maximum or minimum value. And it's maximum when we are moving from positive to negative, which means increasing to decreasing where it changes. Or the opposite, decreasing to increasing where it changes. So this will be the conclusion of our lectures in business calculus, which cover concavity and also covers the point of inflection. As we said earlier, to find a concavity, either concave up or concave down, the first thing we have to, a function will be given, and they will tell us to find the concavity up or down on the function based on some interval. So first we find the first and second derivative of the function. Then we substitute the x value or the horizontal value of the function. If the answer is greater than 0, that means it's concave up. If it's less than 0, then it's concave down. And the point of inflection, we still have to find second derivative. We have to equate the equation to 0. Then we find the value of x, which will be our critical point. And we check whether it's undefined also. Then we follow from there. So again, wish everybody the best for this week. Assignment will be posted soon. And if you have any question, please feel free to post the questions in the Blackboard. Thank you. Bye.